Hello everyone. Today we are going to start our lesson on domain, range, and end behavior of functions. Before we can do so, we would need to know what a function is. A function is a type of relation, and a relation is exactly what it sounds like. It's a relationship between an input and an output value. Now we know it better by the input as being the x value and the output as being a y value. Now a function is a special type of relation where only one x value has exactly one y value. So here on this chart, I have exactly two examples on what is a function and what is not a function. So here we have, these would be considered the x values and these would be considered the y values. Now this one is considered to be a function because we have a list of x's and they go exactly to one y value. Whereas over here, these x values and y values, we have this one, the one that is going to two y values. That means that if I were to put this as coordinates, I would have the coordinate 1, 0 and the other coordinate as 1, 15. You see that the x's would repeat. And in order for a relation to be a function, the x's cannot repeat because it would only go to one y value. Now first we're going to talk about domain and range. Domain is defined to be a list, basically, of all of your x values for which your function is defined. So let's say if I was concentrating on this over here that is a function. If I were to list the domain, I would first open up a set. And we do a set by first opening it up with a brace. And then we would make a list of all of the possible x values that are in my function. So those x values are -3, -2, -1, 0, and 1. So that would be the domain of my function. The range, however, is all of the y values, your outputs. So we would look at the y values and we would open a set and make a list of all of those y values, which are -6, -1, 0, 3, and 15. Now, as we move on in this course, this is very basic because we're given a chart, so we just make a list. However, for our purposes, we're going to be looking at graphs. And for our graphs, domain and range is not written as a list. We write them as intervals. So, for example, if I were going to try to make a list of all of the x values in this function, I would have -6, -5, -4, -3, -2, -1, 0, 1, and 2. But not only those, but all of the decimals and fractions that are in between those x values. If I were to write a list like we did before, that would be an incredibly long list. So instead, what we do for the domain, we would write an interval. What is the x value where my function starts? And from the graph, we look at the smallest x value, which is -6. So we would write that the domain starts at -6, and then it would end at the largest x value, which is 2. So this is my interval from -6 to 2. And that means if I tell you the interval where it starts to where it ends, I am letting you know it's also all of the numbers that are in between in order to prevent from me writing a really long list. For the range, we would do the same thing, but now we're looking at the y values. So we would state, okay, the smallest possible y value on my graph is -1. So my range is going to start with -1. And then we would look to the largest possible value, which is 3. So therefore, the range of this graph starts from when y is equal to -1 all the way up to when y is equal to 3. And that means it's also all the y values in between -1 and 3. Now, when we're writing these intervals, there is a particular way of doing so. There are two types of notation that we're going to use to describe our intervals. There's something called set notation and another called interval notation. Now on this slide, you're going to see a lot of information. And all of it you can read on your own. It's just more detailed in terms of what I'm going to explain, but I'm going to break it down for you. Okay, so there are two types of intervals. We have finite intervals and infinite intervals. Finite means that there are endpoints, meaning it starts at a number and it ends at a number. Now, if you notice this notation, okay, set notation always starts the same way. It starts with the brace first, then you have to define the variable. So here I put x. Now this means if I have an x, this is domain. If it were range, I would write my set notation starting with y. Then I would write where it starts to where it ends. And you would put these symbols in between, the less than symbols, to indicate that x is somewhere between the first value and the second value. Now, in the previous example, we saw that we had these solid circles. Solid circles mean that the number is included, so we have that line underneath. Because that way it means that x is both greater than or equal to that first value, as well as x could be less than or equal to that second value. In interval notation, you don't have to define any variables. In fact, we just state where it starts to where it ends, and then we would use brackets and parentheses to indicate whether whether that value is included or not. If the value is included, we would use a bracket. If the value is not included, then we would use parentheses. Now for infinite intervals, I have two examples here. We have for when our domain, or in this case domain because the variable defined is x, starts at a number and then it goes on forever in the other direction. And in order to indicate that we know it goes on forever, we write the symbol for infinity. So this means that my graph must have started at some number and then it went forever to the right, meaning infinity. And in interval notation, this is actually incorrect. You see how this line is underneath? That means that that value a is included. So this should actually be a bracket. And then if it goes on to infinity, we would put infinity and never include it. We always put a parentheses. And this is because infinity is not a real number. I can't put a dot on infinity, therefore I can't include it. So we always put parentheses. In this particular example, this means that the graph opened up forever to the left. So it starts at negative infinity. That's your least possible x value. And then it went forever to the right. So, not forever. It stopped at a value on the right side, which is included. So see here in interval notation, we have a parentheses, negative infinity, comma, and then that value, and we would close it with a bracket. Now just to reiterate, and here everything is summarized for you, set notation uses inequalities to represent intervals. The easiest way of setting up your set notation is always to write your variable in the center and use your less than symbols. And then if you always write the smallest value on the left and the largest value on the right, your inequality will make sense. And this is all broken down here for you, where less than and greater than means that the value would not be included. And if you have the line underneath, that means that value is included. Now it's important to note that what we're learning is a language. So all of our notations, even though it looks like a bunch of symbols and numbers, do basically state a sentence. So in this set notation example, this could be read that the domain, which is why I have the variable x, and we put the bar here to symbolize that I am done defining my variable. Now I'm going to tell you the interval for my domain. So this is saying the domain of my function is from -3 until infinity, where -3 is included. So it does translate to information for us. And then in interval notation, if I were to translate that, I would put a bracket for the -3, comma, infinity, and then parentheses, because you can never include infinity. So before we start looking at some more complicated graphs, we're going to practice writing out, let's say we're going to focus with domain, since these are going to all represent x values, and we're going to write each one of these intervals in both set notation and interval notation. So every set notation starts the same way. I would open a bracket, define my variable. We're doing domain, so I'm putting x. You put a bar to signify, okay, I'm done defining my variable. Now I always set this up the same. I put my variable in the middle, less than, and close. I'm going to look at my line here, my line segment, and I see that it starts at -5 and it ends at +4. Additionally, these are solid circles. That means that those numbers are included. So I would put the line underneath my inequalities, and that is set notation. Once you have your set notation, you can translate that to interval notation. Because the -5 is included, I am going to put a bracket. Then I would write starts at -5, ends at 4. The 4 is also included, so I put another bracket. In this second example here, if I were to write my interval, I would open up my brace for set notation, define my variable, bar, and again, this should become routine. I put less than, starts at -7, ends at 5, close parentheses. Bracket. Oh my goodness, brace. Now when I look at the numbers, the -7 is not included, so I'm going to leave it as the less than symbol. But the 5 is included, so I'm going to put the line underneath to signify that x could also equal to 5. Now when I translate it to interval notation, since the -7 is not included, I would put parentheses, -7, comma, 5, and since 5 is included, I'd put a bracket. Moving on to our infinite intervals, you see that this particular line here has this side an arrow, signifying that it's going forever to the left. So this would be considered negative infinity, because as we go on forever to the left, those numbers become more and more negative the farther out you go. So when I'm writing my interval in set notation, again, open the brace, define the variable, put your bar, variable in the middle, less than. It's going to start at negative infinity and it ends at 3. Since 3 is included, I put the line underneath and close my brace. For interval notation, this would be a parentheses, negative infinity, comma, 3. 3 is included, so bracket. In this final example here, we have now where it's going on forever to the right. This would be positive infinity, because the further out to the right you go, the more positive the numbers become. So our set notation, we would open up our brace, define the variable, bar, x in the middle, less than. You see that the line here starts at 2 and it ends at positive infinity. 2 is not included, so I'm not going to put the line underneath. And infinity is never included either, so we would leave it like that and close the brace. In interval notation, because nothing is included, I am going to use parentheses for both. So parentheses, 2 to infinity, close parentheses. Now it's very important to note that a lot of writing domain, range, and end behavior has to do with the proper notation. And everything is very detail oriented, so we must be very careful about whether we're using parentheses or brackets. Now here we have a question. We have the symbol U, it looks like a U, represents the union of two sets, meaning it's this interval and this interval as well. Okay, so we'll see that later on as we continue on in the course. So if we're looking at something like this, parentheses, negative infinity, comma 0, close parentheses, union, parentheses, 0, comma infinity. And I want to know, what does this represent? Well, it looks like we're starting at negative infinity, going to 0, and then starting at 0 again, and going all the way to positive infinity. But notice that 0 has parentheses rather than brackets. Okay, if there's parentheses, that means that the 0 is not included. So something was going on in this graph, and it means that the domain of this function would be all real numbers, so everything, except 0, because 0 is not included. The last thing we're going to review before we start looking at graphs is end behavior. Now, our graphs we read our graphs like we read a book. We read it from left to right. Okay? For domain, whenever you're trying to find the domain, like I said, left to right, since domain is all of the x values. So we always want to write all of our intervals from smallest to largest. The range, however, since it's the y's, I would look from the bottom up, because again, since I want to write everything from smallest to largest, if I start at the bottom, that will give me the smallest possible number, and to the largest possible number. Now, end behavior is exactly what it sounds like. It is how your graph is behaving at the ends. Every graph, almost every graph, has two end behavior statements, the one on the right side and the one on the left side. So what I have here are the two end behavior statements that would describe that graph above. Every end behavior statement starts off in the same exact way as x, and then this arrow means approaching. So that's what that symbol translates to, as x is approaching negative infinity. Now this part of my end behavior statement tells me what side of the graph I am looking at. If x is approaching negative infinity, the x's are negative on the left side of the graph. So this means I am looking at the left side. F of x, as we know, represents the y value of the graph. So you're going to tell me what the y values are doing. If I look here on the left, the y values seem to be going down, and that's why it is negative infinity. So all of our end behavior statements start off in the same way. We're going to specify what side we're looking at, and then we write f of x is approaching, and then this is what you're actually filling in. So the only thing that you have to actually evaluate for is this part of the statement. Everything else is the same. So then if I'm doing the right side of the graph, we would start with as x is approaching positive infinity, because that would be the right side. X's are positive on the right. Now if I look at the right side of this graph, you'll see that the y values are going up. Therefore, f of x is approaching infinity. So now we're going to put everything together. We're going to look at several graphs and write out the domain, range, and end behavior. For the domain and range, we are going to use both set notation and interval notation. For this particular graph, right, remember set notation, we start with the brace, define the variable, domain is x, put the bar, x in the middle, less than, less than. Now when I look at this graph, if it goes to the very edge of your graph, that means that it eventually goes on forever. Now domain, remember, is the x values. So you're going to look at how far left does the graph go and how far right does the graph go. This graph, if you picture it going on forever and ever and ever, it's going to eventually open up to the left forever. So this means that the graph starts at negative infinity. Versus when you look at the right side, this will also open up forever and ever to the right, so it's going towards infinity. And translating this to interval notation would be parentheses, negative infinity, comma, infinity, parentheses. Now the range. The range, when we start with set notation, we're going to open our brace, but instead of x, remember range is the y's. So I have to put y bar. This is indicating, okay, I am now looking at the range. You put y in the middle, less than, and I can see from this graph that the smallest possible y value seems to be 0. Then it goes on forever going upwards. So that means that the highest possible y value is going to go up to infinity. Now, whenever you have a real number, you want to determine, is this number included or not? You see how this graph here, it does touch that y value is equal to 0. So if I wanted to, I can put a point there. That means that it is included. So I will put the line underneath the inequality symbol. When I write my interval notation, I would start with a bracket since 0 is included, comma, parentheses, and then close it, comma, infinity, and close it with parentheses. Now for these end behavior statements, I went ahead and already just left you with the first half of each statement, and you have to fill in the second half. So for this first one, it says, as x is approaching negative infinity. This is the left side of my graph. And then we always write the same thing. F of x is approaching, and now I'm going to look at what my y values are doing on the left side of the graph. It's going up forever on the left. Therefore, f of x is approaching infinity. For this second statement, as x is approaching infinity, that is the right side of my graph. When I look at the right side, I see that it is also going up to infinity, so f of x is approaching infinity. Moving on to the second graph here, this is an exponential function. Now something to note about exponential functions, and you don't have to remember all of this right away, we will be covering exponentials later on in the course, but exponential functions level out. It looks like it's decreasing forever, and it is, but it's decreasing forever at y is equal to 0. It's never going to touch 0, however, it always hovers slightly above it. Okay, so that's important to note that it does not touch. Now for the domain, in set notation, we open the brace, define the variable, start our inequality, and now we look, okay, is this going to open forever to the left? And it does. So I'm going to put negative infinity, and then will it open forever to the right? Which it does. So we would put positive infinity. For interval notation, this is the same as the previous one we did. We do parentheses, negative infinity, comma, infinity, close parentheses. Now we start with the range. I'm going to set up my set notation here by defining my variable and setting up my inequality. My smallest possible y value, remember what I said, it is decreasing, it is leveling out. It's never going to just all of a sudden start going down forever. It's leveling out at 0. So the smallest possible y value is 0. Now remember I said that it's not going to touch 0. So it's all those little decimals that are slightly above it. So I'm not going to include include 0. I'm just going to leave it like that. Then I see that on the right side of the graph, it is increasing forever. So that means that the largest possible y value is going to go up to infinity. When I write this in interval notation, we're going to open with a parenthesis since 0 is not included, comma, infinity, and again, you never include infinity. As we go on to end behavior, as x is approaching negative infinity, this means that I'm looking at the left side of my graph. My y values, f of x, is approaching 0. And this is because since it's not going down forever, but in fact leveling out, we put that it's leveling out here at 0. Notice that your end behavior matches your range, right? If this is This represents the left side, and this represents the right side. So now as x is approaching positive infinity, we would put that f of x is approaching, and I look at the right side and you see it's going up forever, so I would put positive infinity. Here we're going to do one more example. Now it doesn't matter that in this one we have stuff going on in the middle. You're still always just going to look at the same, the left side, the right side, how high, how low, that everything goes. And it doesn't matter that it's curving in the middle. For the set notation for domain, we open the brace, x, I'm going to set up my inequality here. And we can see that even though it seems to be kind of opening upwards, it's still also going to the left. You see how it's kind of like diagonally opening? So it will forever eventually open up all the way to the left. Just like over here, even though it's going down, it is also opening to the right forever. So the domain is going to be from negative infinity to infinity. And an interval notation, like in the previous examples, is parentheses negative infinity to infinity, close parentheses. For the range, open up the set, we would put y, the bar, and I'm setting up my inequality here. I notice that on this graph, it is going down forever. That means that it's going to negative infinity for the range, and it is also going to go up forever, so the largest possible y value would also be positive infinity. And in interval notation, it's negative infinity to infinity. For end behavior, we're almost always going to have two statements. We're going to have the one that's to the left, so as x is approaching negative infinity, f of x is approaching, now I look at my graph, and on the left side, my y values are going up, so I would put that f of x is approaching infinity. For the end behavior to the right, we would start with as x is approaching infinity, f of x, and on the right side we see that it is going down, so we would put is approaching negative infinity. Now we're going to look at how to graph lines with a given domain. Now if you recall, the equation of a line is y equals mx plus b. And from geometry, we learned that lines go on forever in both directions. However, here we are given a specific domain. And on this domain, we want to graph the line only from -4 to 4. Okay, so that's what we're going to do. Now, if you don't remember how to graph lines using y equals mx plus b, you can always use the domain to help you figure out how to graph the line. This -4, this represents your first x value, and this +4 represents your second x value. So what I can do is I'm going to take this x value and I'm going to plug it into my function. So I'm going to do f of -4. This is function notation, and it simply means I want to know what the y value is when x is -4. So I'm going to take my equation, which is 3 over 4 times -4. Remember, when you multiply by a whole numbers are always over 1, plus 2. When you multiply fractions, remember it's numerator with numerator, denominator with denominator. So this would give me -12 over 4 plus 2. -12 over 4 is -3 plus 2, which then is going to give me -1. That means that I have the coordinate -4, -1. So I'm going to go ahead and plot that point. That is the very first point of my graph. Next, I'm going to plug in the second x value that was given to me. I'm going to find f of 4. which will equal to 3 over 4 times 4 over 1 plus 2. A shortcut with fractions, if you ever notice the same number diagonally across, they just cancel and you can turn them into ones. So 3 times 1 is 3, 1 times 1 is 1, and 3 over 1 is 3. And then we have that plus 2. 3 plus 2 is 5. So the coordinate that I'm going to plot is 4, 5. Once you have your two endpoints, you're pretty much done. You would just go ahead and connect your dots. And this is drawing my line on that restricted domain. Now the range, we're going to look at the y values. The smallest y value is -1, and I'm going to write this in interval notation. So I would put a bracket, -1, comma, and then the largest y value, which is 5, and close it with a bracket. Whoops, I forgot to answer a question here. Sorry about that. This question reads, how would the graph change if the domain was parentheses -4 to 4 instead of bracket -4 to 4? Now, if it was a parentheses, that indicates that these endpoints would not be included. So what I would do is, instead of that solid circle, I would use an open circle instead. Now we're going to move on to the next example. For this particular example, we are given the line -x minus 2, and we are going to graph it with the domain from -3 to infinity. Now in this particular case, we have the smallest x value, and then it's going to go on forever to the right. So what I can do is I can graph first the coordinate that goes with -3. So I'm going to go ahead and plug it in to my equation. So I'm going to find what is f of -3. -3, because we have this negative here, this becomes a +3, minus 2. This gives me the y value of 1. So the coordinate that I'm going to plug in is -3, 1. Now notice that -3 is not included because it doesn't have that bar underneath. So I'm going to go ahead and put an open circle. Now in this example, it does open up forever to the right. So since I don't have an endpoint, since it's going to the right, if you want to just plot one more point, you can pick a number that is to the right of -3. Let's say I choose 0. I am going to plug in x is equal to 0. That means that we would have -0, which doesn't exist, is just 0, minus 2. And that gives me -2. So the coordinate that I'm going to plot is 0, -2, which is right here. Once you have your second dot, and since I know it goes on forever, I am just going to connect and then keep going. And this would be that function drawn on that restricted domain. So now for the range, we're going to write it in set notation. So I'm going to put the brace, define my variable as y. I'm going to set up my inequality here. The smallest possible y value, see how it goes down forever. So that would be -infinity. And then the largest possible y value is this one right here, which is 1. And since that's an open circle, I would not include that 1. Now for this question, it says, what is the end behavior as x increases without bounds? If x is increasing, that means that I am looking for as x is approaching infinity. This is the right side of the graph. As x is approaching infinity, f of x is approaching. Now I'm going to look at my graph. On the right side, I can see it's going down, so I would put negative infinity. Now this follow-up question states, why can't we talk about the end behavior as x decreases without bound? If I look on the left side of the graph, because that's what this is talking about, on the left side, notice that it doesn't keep going. It ends here at -3. Therefore, this is bounded at the left side. Meaning that there is no end behavior on the left. Moving along, we're going to look at how to continue graphing a line on a restricted domain, but now we're going to add on to that, meaning that we're going to look at a situation in verbal description of a line, and we're going to answer some questions regarding it, including domain, range, and how to write the equation given that information. So we're told in this example that a candle is 6 inches high and it burns at a rate of 1 inch every 2 hours. So this right here, whenever you see some unit of measurement over time, that's going to be the rate. And a rate is slope. So this is going to be the slope of my line. And it's burning for 5 hours. Now, as you remember, equations of lines are written as y equals mx plus b. So eventually we're going to make sure that our line fits this format. First and foremost, the candle's burning rate is, since it says here 1 inch every 2 hours, that's going to be 1 inch every 2 hours. Additionally, because this rate means that the candle's height is going to decrease, that means that the slope will be negative. Now the candle's height h in inches at any time t in hours is modeled by, and then this is where we're going to write the equation of our function. Notice that it's written in function notation, h of t. Remember that this represents the y. And now I'm going to fill out the rest of my equation. So since we know that the slope is -1/2, that is m. And instead of writing x, I see here that on my axis, we define the x-axis to be actually t. Then plus my y-intercept, because that's what b represents. And from the verbal description, we see that the candle is originally 6 inches high. This is the y-intercept. So overall, this is the equation of my function. H of t is equal to -1/2t plus 6. On a side note, I would like to point out that the y is h of t because we're using the variable that is defined to be the y-axis, which is h, to signify the height. Now, since the candle burns for 5 hours, the domain is restricted to the interval 0 to 5. This is the domain of our function. Okay, it starts burning when the time is 0. There's no such thing as negative time. And it stops burning at 5. Now, because these are real times, we would include these values. Now that I have my domain and the equation and the rate and all that, I can actually go ahead and start graphing. Now we know that the y-intercept is 6, so I'm going to put my first point on the y-axis at y is equal to 6. Next, I need my second point. Now because the domain is restricted from 0 to 5, what I can do is take this 5, which is where my line is going to end, and I'm going to plug it into my function. So, which is what we did in the previous slide. So we're going to do h of 5 is equal to -1/2 times 5 plus 6. And when we work this out, half of 5 is 2, so negative 2.5. And then when you add 6, we get 3.5. This means that we're going to plot the coordinate 5, 3.5. So I go to 5, and then the y value, which is 3.5. This right here, this is 3, so just 1 over would be 3.5. And then I could connect my dots here. Oops, and I went off a little bit, but that would be your line. Now we would see what the range would be. Because we used interval notation, we'll stick with interval notation for the range. Both of these values will be included, so I'm going to use a bracket. The smallest possible y value I see is 3.5, and the largest y value is 6. And that's the range of this function. Moving on to our final example. Now I've taken all of those kind of hints away so that we can actually try to do this on our own. And I put here some steps for you to follow. So it says here that while standing on a moving walkway at an airport, you are carried forward 25 feet every 15 seconds. This is the rate. And we're traveling for 1 minute. So first we're going to identify the slope and the y-intercept. Now the slope, as I said, is given to us as 20 feet every 15 seconds, which you can write as 25 over 15. Now since 25 and 15 are both divisible by 5, we can simplify this fraction to be 5 over 3. So this is my slope. And it is positive because the distance that we're on the moving walkway would increase over time. Now we also need the y-intercept. The y-intercept, remember, is your starting point. The moment you step on the walkway when t is equal to 0, time, we haven't moved anywhere. So that means that the distance would be 0. Now we're going to see if we can write the linear equation that models that situation. So remember, a linear equation is y equals mx plus b. But we're not going to use y and we're not going to use x because we're going to define our variables here depending on what it represents. Since the y-axis is distance, I am going to use the letter d to represent y. And since the x-axis is time, I'm going to use t for the x-axis. Therefore, if I were to write the equation of this line in function notation, the y would be represented as d of t is equal to mt plus 0. And now I'm going to fill in with the slope. Sorry, I put plus 0 because the y-intercept is 0. I kind of skipped a step. So the equation of our function is going to be d over t is equal to 5 over 3 t. And since, again, the y-intercept is 0, we don't need to write plus 0. So we've written our equation. Now we're going to graph the function using the equation. We know the y-intercept is 0, so I can put my y-intercept on the graph. And now we're missing that second point, where it ends. So let's go ahead and actually find the domain. And we're going to find the domain using set notation. So I'm going to set up my set notation here by opening up my brace, defining my variable. Since this is domain, I'm using t. I'm setting up my inequality in the center. We start traveling when t is equal to 0. Then it says that we're traveling for 1 minute. But if I look on my graph, time is in seconds, and 1 minute is equivalent to 60 seconds. So we're going to stop traveling at 60 seconds. And since these are real times, I'm going to include these numbers. So now that I know where I finish, I'm going to take that 60 and I'm going to plug it into the original equation. So I'm going to find d of 60 is equal to 5 over 3. And then since I'm multiplying 60, I'm going to go ahead and put it over 1 so I can multiply these fractions. 5 times 60 is 300 over 3 times 1, which is 3, and 300 divided by 3 is 100. So that means that the coordinate that we can plot is 60, because that's what I plugged in, comma 100. So I'm going to go here on my graph. I have 60. I go up to 100. And then I connect the dots. And this would be my line. Our final step here would be to find the range. Again, we're going to use set notation. And the variable that we're using for range is going to be d. Put d in the middle, setting up my inequality. The smallest distance is 0, and the largest distance is 100. And again, because these are solid circles, I'm going to include that. And that's it. This is how we can use this verbal description to find the equation, the domain, the range, and the graph.